It is a present. You can share your screen, sir. Good
Okay,
afternoon,
okay.
participants.
Hello, ma'am. Can you hear me?
Yes, ma'am. Yes, ma'am.
Agila, ma'am, can you hear me?
Yes, ma'am. Yes, ma'am. You're audible.
Okay.
People are joining. Sir, people are joining, sir. We'll start in a minute, sir.
Okay, okay.
Anita, ma'am, shall we start the session?
Yes, madam. We shall start.
Yeah, people are joining. So I think, I hope they
Yeah.
may join soon.
Can we
Like
wait for another 5-10 minutes so that not even 5-10, 5
2
minutes so that
minutes. Yeah, 2 to
50
3 minutes
people,
you can.
if
Hmm.
50 people joined, we will start.
Yes, okay.
Good afternoon, Sathiesh sir.
Good afternoon.
Okay.
Ma'am, I hope that we can start, right?
Yes, ma'am. Yes, we'll start. I think 51 participants are there. Right. Very good afternoon, participants. Welcome you all for the last day of our 6-day online FDP on demystifying transformers, the brains behind generative AI. It's my privilege and honor to welcome and introduce our speaker of the day, Dr. V. Sathiesh Kumar, MIT Anna University, Chennai. Dr. V. Satish Kumar sir has been working as an assistant professor, selection grade in the Department of Electronics Engineering, MIT campus, Anna University, Chennai, since 2014. He is also acting as a Deputy Director, Planning and Development and RUSA Coordinator, Anna University. He has about 13 years of teaching experience at Anna University and various affiliated engineering colleges of Anna University. He received his PhD from Department of Engineering Design, IIT Madras, Chennai, Tamil Nadu in 2014. His research interest includes artificial intelligence systems, embedded systems, optoelectronics, machine learning, computer vision, laser remote sensing, and laser spectroscopy. He has published 94 international research works, comprises of 27 journals and book chapters of 8 numbers, and 59 conference publications. And he also had an honor of having 4 patents with 2 granted and 2 published. The publications involved reputed journals with high impact factor, namely Engineering Applications of Artificial Intelligence, Expert Systems with Applications, Ecological Informatics, Journal of Applied Spectroscopy, Journal of Optics and Laser Technology, Journal of Intelligence Systems and Fuzzy Systems, Journal of Physics and Applied Physics, etc. He also presented his research findings in the international forums organized in various countries such as Mexico, Italy, France, Japan, Spain, and Greece. Given his expertise in this domain, we requested Sad to give a talk on vision transformers. He also kindly accepted and is with us today. I'm sure you will enjoy his session on vision transformers. Over to you, sir. Happy learning, participants.
Thank you, ma'am.
Thank you, sir.
Thank you for your introduction. A very good
Sir,
afternoon to
if possible, kindly turn on your camera, sir, for a snap.
just a minute.
Sir, the screen can be made visible, sir.
Now it is civil, ma'am.
No, only
Fine.
one at a time.
Yeah.
Yes, now you can, ma'am.
Thank you, sir.
Okay. A very good afternoon to all the participants of this FDP. So today I'm going to talk about vision transformers for image classification. So you might have heard a lot of lectures in this FDP on transformers, and I'm going to especially talk about vision transformers little bit in detail. How it functions in detail, I try to describe in this lecture. So the vision transformers are used in computer vision applications such as image classification. So image classification in the sense when we try to provide an image to a computer, it will try to assign a suitable label to that image based upon the categories which we provide to the computer. So we will give some categories to the computer. It will pick an appropriate label and it will try to assign to that particular image. Then we talk about object detection. So object detection is a process in which the objects in an image or a video can be identified. Then this vision transformers can also be used for semantic image segmentation process. So for example, in an image, if it contains many objects and we can do semantic image segmentation, means the object based segmentation can be done. So by assigning labels for each and every pixels, so thereby we can able to do object based detection in an image is possible using a vision transformer. So it acts as an alternative to convolutional neural networks. So I will give just a little bit of gist about convolutional neural network. So convolutional neural networks are very popularly used for doing your image classification part. So where we take an input image, so this input image is given to a convolution layer. So this convolution layer will try to extract the features from the input image. Then in order to reduce the dimension of the extracted features, we make use of a pooling layer. So this pooling layer, what it does, it will reduce the dimension of the feature matrix. Then if we want, we can include as many as convolution layers and as many as pooling layers. Then at the last, in the last pooling layer, we have the features extracted from our input image in a smaller dimension format. So this feature extracted matrix can be flattened and it can be given to a fully connected layer. So this fully connected layer is nothing but a neural network. So this neural network will be used for determining the output of this model, or it will try to give the category of the input image which we provide to our model. So that is how the image classification is being carried out by a convolutional neural networks. So there are many popular image recognition or classification models are available. Some of them are ResNet, VGG. In VGG itself, we have VGG 16, 19. So like that, multiple types of architectures are available. So these architectures are especially used for your image classification part. In order to do object detection, we have other architectures like YOLO V3, V7, V8, V12. So there are many such object detection architectures are available. To do semantic image segmentation, we can use something like a segment anything, unit architectures, etc. So all these architectures are developed based upon your convolutional neural networks. So now we are going to talk about a vision transformer, which is going to do this classification. So what is the advantage of using a transformer? It provides at least 4 times the computation efficiency and accuracy in terms of the performance when compared to your CNN model. So it has a faster computation and it can produce a very good results. And you might be knowing this transformer models are used in the ChatGPT based applications. Now let us see how this vision transformer is going to work. First, I will give a short description about this vision transformer. Then we will try to go in detail one by one as per the blocks given. So first let us take an input image. We take an input image. We divide this image into smaller sections. So this we call it as a patches, image patches. So this is image patch 1. Next one is image patch 2. So like that, we need to divide the image into small patches. In this case, our image is divided into 9 patches. Then we try to arrange this 9 patches in terms of a sequence form. So sequence form in the sense, this is top left, next one is top middle, then top right, then middle left, middle right, then bottom left, bottom middle, and bottom right. So like this, we are trying to arrange this image patches in terms of a sequential order. After doing it, we try to take this image patches, convert it into a vector. So let us assume I'm going to convert each image patch in terms of a 512 dimension vector. So 512 dimension in the sense I have 512 elements in a vector. Okay, so the number of elements in a vector is going to be 512. So each image patch is converted into a 512 dimension vector. Then for each of this image patch vectors, I'm going to add the positional information. So you can see here the numbers 0, 1, 2, 3, 4. So like that it goes on. So this represents the position of each vectors. And then we try to provide the input to your transformer encoder part. And then it goes into a multi-layer perceptron, where this multi-layer perceptron will give the classification output. So this is an overall picture of your vision transformer. Let me repeat it once again. So we take an input image, divide it into as many sections as possible. We can divide. Then we take the patch, convert it into a vector. So here we are converting each patch in terms of a 512 dimension vector. Then we try to add the position information to this vectors, then give it to a transformer encoder. So this transformer encoder will find the relationship between the patches, and then based upon that, the output will be produced. And this output goes to a multi-layer perceptron, which is again nothing but a neural network. So this neural network is going to classify the input data depending upon the classes which we provide to it. So this is an overall introduction about your vision transformer. So now let us take segment by segment and we try to see. So when you look at this transformer encoder part, what is there inside this transformer encoder? So this transformer encoder block is given here. This data from your patches. Okay, so this patches data, so which is coming here at this point, goes into this transformer encoder. Inside the transformer encoder, first layer is your normalization layer. We try to normalize the data. Then we try to do multi-head attention mechanism. Multi-head attention mechanism helps in finding the relationship between the patches. If, for example, how the first patch is related to second patch, how the first patch is related to third patch, fourth patch, fifth patch. So like that, we try to find the relationship. So there we get the attention mechanism. Once it is done, so like that, we have to do it for each and every image patches. For example, bottom left patch, how it is related to all the other patches. So like that, we try to get the attention mechanism. Then after getting this attention mechanism, again we do normalization, and then it goes into a multi-layer perceptron. So this multi-layer perceptron is a feed-forward neural network, which is inside your transformer encoder. So remember, this multi-layer perceptron is different and this multi-layer perceptron is different. So this multi-layer perceptron is inside your transformer encoder. There is another neural network which is outside your transformer encoder. Then it produces an output. And this output goes to a ML, multi-layer perceptron, to produce the class labels. Now let us go step by step. How to classify an image. So as I said, we took an image, we divide the images into patches. So for example, let us take an image and I have divided the image into 3 patches here. I have divided the images into 3 patches here. So 1, 2, 3. Then what we do is we are going to convert this image patches into a vector. For example, how this can be done? I can take the pixel values and I can represent it as a vector, or I can use some feature extraction algorithms, get some extracted features. That features I can use it as a vector. So like that, we can use any type of mechanism to represent a vector from an input image. So here let us assume I took an image and the output of this image which I'm going to get is going to be 4-dimensional. For simplicity, I'm taking it as 4-dimensional, only 4 elements in this vector. Same way for the second image also 4-dimensional vector. For the third image patch also, it's a 4-dimensional vector. So now we are going to put the position encoding. So position encoding, the sense I'm going to say that this patch is the first patch and the second patch, third patch. So and the first, after the first patch, the second patch comes. After the second patch, the third patch comes. So like that, we are going to provide the sequence. So here the sequencing is not going to be in terms of a number. As I say, the first sequence, second sequence, third sequence, or first image patch, or second image patch, or third image patch. What we are going to do is we are trying to put the patterns to this input image. So these patterns will act like a position vectors. So for example, one of the pattern is, since my input is 4-dimensional, my pattern is also going to be 4-dimensional. So here I took 0, 0, 1, 1. So if I try to represent it as a graph, you will get something like this: 0, 1. This is 0, this is 1. So this is the pattern which represents the first position, right? So like that, we are going to provide the patterns for each and every position. When I take the second pattern, here I take something like 0.84, 0.84, it goes to 0.01, then it comes to 0.54, then it goes to 1. So this is one pattern, right? So this is 0.84. This will be 0.0001 and this value will be 0.54 and this value will be 1. So this is the pattern which I'm going to use it for the second image patch. Same way, if I take a third image patch, I'm going to use another pattern, again 0.91, then it goes to 0.02, then it goes to negative, okay, 0.042, and it comes to 1. Okay, so this is 1, this is minus 0.42, this is 0.0002, and this will be 0.91. So like this, we can use the patterns for different positions, right? And these patterns can be added with your input data to create a vector which we are going to give it to your transformer model, right? So this is one example to understand how the position information is embedded into your input vector. So there are different patterns available. So one commonly used pattern is going to be like this, which is made up of sine wave and cos waves. Here you can see the patterns. So here I have taken 512 dimension vector. It starts from 0 to 501. So our input dimension is 512 dimension input vector. Then I'm going to create a pattern of size 512 dimension. So let us assume I have 20 sequence or 20 image patches. So this is for image patch 1. This is for image patch 2. Like that it goes on till image patch 19. Right? So 20 image patches are there. Let us assume. Then I'm going to take for the image patch 1, this is the pattern which I'm going to take. So the value for this color coding is given here. So my value is going to vary between -1 to +1. You can see here at the middle point, the pattern changes because this first part up to some 255, we use sine function to generate it. After 255, we try to use a cosine function. So there are two formulas here, sine based formula and cosine based formula. Using these formulas, we can generate these patterns. And each pattern is represented by a floating point numbers. And these patterns will be added with the image patch data. So here this formula is given by PE position, comma 2i, where I is the dimension, right? For which dimension I'm going to estimate the value, right? So for example, this is 512 dimension. I'm going to estimate a value for 175, right? So I will be 175. Okay, if I put I 175, then position is for which image patch I'm trying to estimate. So let us assume I'm going to estimate for image patch 2, right? So this is the position I'm going to estimate. So position will be 2. Right? So if you plug in the values, you will get a value. Okay, so that will be the value for this point. Okay, at this point, this will be the value. So like that, we try to estimate for all the 512 dimensions. So thereby you will get a waveform like this. So this is how the position information can be generated, and this information can be added with the input data from your image patch. Okay. So after doing this, after embedding your position information with your input data, we are going to give it to a encoder blocks. In Vision Transformer, a famous paper, Attention is All You Need, in that paper, they have described the encoder block with 6 stacked versions. So we will have 6 encoders. For example, here I have a encoder block 1, encoder block 2, encoder block 3, like that it goes on till encoder block 6. So in that paper, the first paper where they introduced about the transformers by Google, they try to put 6 encoders. And all these encoders are identical in nature. Right? So let us take one encoder and we will try to see what is that inside this encoder. Right? So here I take the inputs. These inputs are what? Your input from the image plus your positional information. Right? So that is the input which we are getting here. And we get this data for each and every patch. If I have some 9 patches, I will get 9 512 dimension data. If I have 20 patches, I will get 20 512 dimension data. So it goes into a encoder block. In this encoder block, if you see, you have this multi-head attention block, which will try to see how these patches are related with each other. How the first patch is related to second patch, third patch, fourth patch. So how many patches are there? It will try to find the relationship. So which patch gives more information to the current patch? So that we try to identify with the help of a multi-head attention block. Then it goes into the another important layer, which is your feed-forward neural network. Each patch data goes into a feed-forward neural network. and then it will produce an output. That output will go as an input to the encoder 2. So again in encoder 2, we will have the similar blocks. Then again, the output of encoder 2 will go to encoder 3. Output of encoder 3 will go to encoder 4. So like that, it goes on till your encoder 6. Encoder 6 output, it goes into your multi-layer perceptron, where this multi-layer perceptron is going to provide the class categories of the input data. So the important things here is all the encoders are identical in nature. And another important point is this encoders, even though they are identical in structure, they do not share the weights. Okay, the weights are not shared between these encoders. So if you see the encoder, there are two important sublayers. One is multi-head attention layer and feed-forward neural network. So what is the use of this multi-head attention layer? It helps the encoder to look at other words or image patches in the sequence as it encodes the current patch. Right? So this is applicable for both your image as well as the text sequence. Right? So this encoder block, what it does, it will try to look at the current patch and it will try to find the relationship between the other patches. And after doing this, it goes into a feed-forward neural network, which is independently applied to each position. Each image patch has a separate neural network structure. Even though the structures are same, each output of your multi-head attention will go to a separate feed-forward neural network. Thereby, the computation will happen in parallel fashion. Since it is in parallel, the speed of execution will be very fast in case of your transformers. So that is why the computation time is greatly reduced in a vision transformer when compared to your CNN. So let us look at the details. We take image patch, represent it as a vector, then add the positional encoding. So positional encoding in the sense, for position, we use some patterns. After doing that, we get the output. That output goes to your encoder. Let us take, I have encoder 1. It goes to this encoder. In the encoder, we have a multi-head attention block. So this multi-head attention is made up of many self-attention blocks. Right? So let us try to understand what is this self-attention block, how it is going to be done. Right? So here you can see it is represented in terms of a vector, image patch, x1, x2. Then after positional information is added, again we have x1, x2. So this x1, x2 goes to your self-attention block. So this self-attention block, what is going to do? It is going to find the relationship between the image patches and it is going to generate individual outputs for each patch. So Z1 is an output for X1. Z2 is an output for X2. So like that, separate outputs are generated from the self-attention block. Then what we do? We try to add this Z values with your input data. And we try to do normalization part. So you take the X values. So X values are coming from here. Z values are coming from here. Right? So both we try to add and then do normalize. So this step helps in reducing the vanishing gradient problem. Right? So usually when I have large number of layers, what will happen? Automatically, when I try to do a back propagation, the gradients will try to go to 0. So in order to avoid that, what we do is we try to take the input, small amount of input, and feed it to the subsequent layer. So thereby the gradients will not get vanished away. It can remain in a stable position. Then after doing this add and normalization, what we do? We send this data Z1 for image patch 1, Z2 for image patch 2. It goes into a feed forward neural network. So here only I said that we have separate feed-forward neural networks for each image patch. Right? In self-attention, there is a sharing of information between the image patches, but it does not happen in your feed-forward neural network. We have a separate neural networks for each and every input patch. And then again, we try to do add and normalize, and it will produce a output. So this encoder 1 output will go as an input to your encoder 2. It will go to your encoder 2 input. Again, encoder 2 output will be given to your encoder 3. So like that it goes on. So that is how these transformers are built. So there are dependencies between the input parts in the self-attention layer. So that is what I said. In the self-attention layer, the images share the information. By sharing the information, we can find the relationship. Whereas in feed-forward layer does not have those dependencies. However, the various parts can be executed in parallel. That is what I'm trying to say here. So this input patch 1 can get executed. At the same time, input patch 2 can also get executed. Right? So thereby the execution speed will be fast, since the computation is going to happen in a parallel fashion. This residuals in the sense we try to use the input data again and again to the layers. So why this is done? So this is done to avoid your vanishing gradient problem. Okay. Now let us talk about this self-attention block. Now I'm going to talk about this self-attention block. What happens in this self-attention block that we try to see. So in the self-attention layer, first thing, our input data. Let us assume we are going to have a 512 dimension vector for an image patch. Okay, for each image patch, I'm going to have a 512 dimension vector. Let us assume we have 2 image patches. Image patch 1, image patch 2. So image patch 1 is represented by a vector x1. Image patch 2 is represented by a vector x2. So this vector is nothing but a 1 row, 512 columns. So it is called as a 512 dimension vector. Same way x2 is also 1 by 512. So now what we are going to do is we are going to generate 3 matrices. One is called query, key, and value. So 3 matrices we are going to generate. So this query means it represents the current patch. Okay, it represents the current patch. Key, it represents the content of each patch. Okay, it represents the content of each patch. And value is nothing but the actual information or content in that particular patch. Right? So we are going to generate 3 matrices, one for query, one for key, one for value. Query will represent the current patch. Key will represent the content. Okay, it will not represent the patch, it will represent the content, and the actual content will be in the value. How to generate this query, key, and value? We will take this input data, multiply it with your matrix, WQ matrix, WK matrix, and WV matrix. Let us take this matrix to be of size 512 by 64. So when I take my input data, which is 1 by 512, when I multiply it with 512 by 64 matrix, my output will be of 1 by 64. My output will be of 1 by 64 matrix. So that is what we get here, Q1, Q2. Same way, if I multiply my input with WK, I will get K1 and K2. Input with WV, I get V1 and V2. Now, how to get this WQ, WK, WV? How to get this matrices of this size? This we don't know, right? So what we do, we try to do a random assignment for this matrices. So WQ, WK, and WV all are assigned in a random fashion. So after assigning it in a random fashion, we do a multiplication. Thereby, we get a query matrix for X1, query matrix for X2, same way key matrix for X1, key matrix for X2, value matrix for X1, and value matrix for X2. Right? So this is how first this three matrices are generated. Remember, query means it represents the current patch. Okay, it represents the patch. Key represents the information, right? It represents the information, whereas the actual value is where in the value matrix. So key is something like an index. So index and its values are provided. Okay. So now we have generated these three matrices. So we took image patch 1, image patch 2, convert it into a 512 dimension vector. Then we generated this query matrix, which is of 64 dimension. Key matrix is of 64 dimension. Value matrix is of 64 dimension. Right. So this we generated for image patch 1 and also image patch 2. And the next step is to determine the score. So what is the importance of the score in the sense? Here only we try to see how one patch is related to another patch, how the other patches contribute for this current patch. So that we try to see. So in order to do that, what we do is we take the query patch. So Q1 represents the image patch 1, right? So we take the Q1, take a dot product with K1. Okay, Q1 dot product with K1, we get a value. Same way, this is my query and I want to see how it is related to the subsequent patches. So I take Q1 dot product with K2 we try to do here. So thereby we find the relationship between image patch 1 and image patch 2. So we get a value here. If I have subsequent patches, you have to do Q1 dot K3, Q1 dot K4. So like that it goes on depending upon the number of patches you are going to consider. Same way for image patch 2 also you have to do. So for image patch 2, how it will get varied? First one will be your Q2 dot K2. You will have some value. Then now we have to see how this Q2, now this query patch is Q2. How this query patch Q2 is related to your image patch 1 we have to see. So we have to compute Q2 dot K1 also. So that is how we try to see the relationship between the image patches. So score is an important parameter which determines how much focus to place on other parts of the input sequence will be given by the score. Score determines how much focus we have to put on other sequence parts. So the score is calculated by taking the dot product of the query vector with the key vector. Right? So this you should remember. Next step, after computing the score, what we do? So now we got some values which says that how one patch is related to other patch. That is done by your score value. So in order to scale it down, right? In order to scale it down, what we do is we divide this value, we divide the score by root of dk, where dk is the dimension of your key. Okay, dk is a dimension of your key. So dimension is, it is 64 dimension. Key is your 64 dimension. So if I take root of 64, it becomes 8. Okay, so it will be 112 by 8. When I do that, I will get 14. Same way, 96 divided by 8, you will get 12. We try to scale down the values. Right? Instead of using a large numbers, what we are doing, we are trying to scale it down by dividing the score value by root of dk, where dk is the dimension of your key matrix. So after getting the scale down value, I want to represent this score in terms of your probability. So that is done with the help of a softmax activation function. So softmax activation function is given here. E power zi divided by summation j equal to 1 to k e power zj. So we have two values. One is 14 and another one is 12. So we have to compute. How to compute? For 14 computation, what we do is we take e power 14 divided by e power 14 plus e power 12. When you do that, you will get 0.88. Same way, how to compute the value for the second element, 12? We take e power 12 divided by e power 14 plus e power 12. When you do that, you will get this 0.12. So now we have turned this score matrix into a probability score. So in a probability, when I add all the values, it should be equal to 1. You can see that 0.88 plus 0.12, it will turn out to be 1. Okay, so in terms of a probability, we try to assign the score. So that is the subsequent step. So what we do here, first we divide the scores by 8 to scale it down. Then we send that value to a softmax activation function. So softmax activation function, what it does, it turns the score into probabilities. So the softmax score determines how much each image patch will be expressed at this position. If the probability is high for a particular position, then its contribution is going to be high for the current patch. If the probability score is low, then it is not going to contribute much to our input patch, current patch. Right? So that is how we try to find the attention. Right? How this current image patch is related to other image patches. Which patch is going to contribute how much? So that is determined using this methodology. Next, what we do? So this everything happens inside your self-attention layer, right? So we have covered till this point, right? So next, what we do is we try to find the Z. Okay, so Z is the output from your self-attention layer, right? So how we are going to do that? We are going to take the value matrix, right? We are going to take the value matrix, take the probability score, multiply it. Okay, we are going to do a multiplication. So when I do multiplication, I will get a value. Right. So here, if you see here, you can see the color shade here. Here the probability is close to 1, 0.88. So the color remains same. Whereas in the second case, what happens? It is only 0.12. So the color is faded out. Right. So this is for image patch 1 we are trying to do. Right. Image patch 1, I'm trying to put this probability. Okay. So this current patch has a higher probability. So we take the value much more probable, and the other sequence is going to contribute little bit to this patch. So we try to compute V1, V2. So if I have multiple patches, V3, V4, V5, we have to compute. Same way we have to do it for image patch 2 also. So image patch 2, I have to do the computation, and then we have to compute V1, V2, V3, everything we have to do. Then what we do? We have to add all these values. So V1 plus V2 will give you, so this V1 and V2 will give you Z1. Same way for second patch, again you have to do this computation. In second patch, what we will do? So for second patch, here we will be doing Q2 dot K2. Same way, Q2 dot K1 we will be computing. Then what I will do? I have to divide this value by root dk for scaling it down, right? So this value also it should be divided by root dk. Then what I should do? I should apply a softmax here. Softmax activation function. Okay, I have to do a softmax activation function. So thereby I will get some probability here for the image patch. Right now I'm doing it for image patch 2, right? So I will take it as something like x1, not x1, it will confuse. So I will take it as some b1. This is b2, right? So I get some values like this. So this b1 and b2 are probability scores. Then what we do? We multiply this probability score with value. Okay, so this b2 should be multiplied with b1 to get b2. Same way, this b2 should be multiplied with v1 to get this v1. Then add this v1 and v2 to get this z. So like this, we are going to do it for each and every image patches. So this is represented in terms of a mathematical equation. Attention of Q, K, V. Q stands for query, K stands for key, V stands for value, which is nothing but your query matrix into your key matrix. So we take transpose of key, then we scale it down by putting root of dk, and this value is used in your softmax activation function. So we get the probability score, and this probability score is multiplied with v. Right? So thereby we get the attention values. So that is how this self-attention block is going to work. So let me put this together. So let us take two patches, patch 1, patch 2. So this is x1, x2, right? So we try to put it in terms of a matrix format. Okay, same case for your, we take WQ, WK, WV, right? When I do multiplication, I get query, key, and value matrices. Then we take the query matrix and multiply it with the key matrix divided by root of dk, then apply a softmax activation function, then give the probability score multiplied by your value to get the z value. So z first row output for first patch 1, second row output for patch 2. Right? So this is what happens in your self-attention layer. Now, this WQ, WK, and WV, we have assigned these matrices in random. Depending upon these values only, the query matrix, key matrix, and value matrix are generated. If we change this WQ, WK, WV, then automatically QKV will get changed. So this gives an aspect that if some of the assignment is wrong, okay, let us assume we are doing some random assignment. If that assignment is wrong, right, by taking multiple self-attention blocks together, in each self-attention block, we might have done different types of random assignment. So out of, for example, if I take 6 self-attention blocks, out of this, some 4 or 5 blocks, I have assigned it correctly. Maybe probably 1 or 2 blocks I have done some mistake in assignment of this WK, WK, WQ, WK, and WV matrices. So that will reduce the error in our prediction. So when we combine such multiple self-attention blocks, we call it as multi-head attention block. So that is what we are going to do next. So we are going to convert the self-attention block into a multi-head attention block. What is multi-head? I'm going to do the same thing. Okay, so we take multiple attention heads. So this attention head 0 is obtained for this matrix W0 of Q, W0 of K, W0 of V. So thereby we generate this Q0, K0, V0. Then we do all the process. Right? So this gives the output. Same way, instead of this W0Q, W0K, and W0V, if I use some other matrix, W1Q, W1K, W1V, I will get different type of attention to the same image. Right? So I'm going to put everything in a parallel fashion. So that is what you can see here. Right? So we have multiple self-attention blocks. H number of self-attention blocks we are going to have. So one self-attention block will produce the output Z. Here I use 2 patches, so I will get 2 outputs, Z1 and Z2. Same way, the second attention method also will produce Z1 and Z2. So like this, if I have multiple attention heads, I will get multiple outputs. So all these outputs can be concatenated together. Okay, it is concatenated and then it is again transformed into a single matrix. We will see how this happens, right? So I take a input data, give it to multiple attention heads. H0 produces an output Z0. H1 produces an output Z1. H7 will produce an output Z7. So like that it goes, right? So now what we are going to do, we are going to concatenate all these outputs. So we are going to put Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7. We are going to concatenate it. So if the outputs of each attention block is going to be 2 by 64, then after concatenating, it will change to 2 by 512. So that is this block action. Concatenation block is going to do. Then it goes into a linear layer. What does this linear layer will do? So the linear layer, so now I have this concatenated output. I want to reduce this output. Okay, so in order to reduce this output, we are going to take again another matrix, WO matrix. We are going to, this WO matrix is going to be of dimension 512 by 512. So here the input is of 200 by 512. So when I do a multiplication, matrix multiplication, my output will be 2 by 512. So again, how to assign these values for WO? So this is for converting your concatenated outputs from the attention block to a simple output. So when I do this, so this assignment again is going to be your random assignment. So when I do that, it gets converted into a 2 by 512 output. So we are doing a linear transformation here. Okay, linear transformation. So thereby we get the output. So this output is the output from your encoder 1 self-attention block. Okay, here now it is not self-attention, it is multi-head attention. Okay, it is a multi-head attention output. This output is a multi-head attention output. Right. So how we can write this multi-head attention as an equation? So we are going to concatenate the outputs from head 1, head 2, head 3, like that it goes on till head H. Multiply it with WO. Right? Multiply it with WO. So it gives the multi-head output. Z. So now we have talked about the self-attention block. Okay, so let us put everything together in a single slide. Okay, I will just describe it very quickly. We take two image patches, represent it as a vector. So here we have added the position information also. Then we took random assignment of W0Q, W0K, W0V. So this is for attention head 0. Okay, attention head 0. By doing the operation, we generate query matrix, key matrix, value matrix. So then do that process to get the output Z0. Same way in attention head 1, we use W1Q, W1K, W1V, generate Q1, K1, V1, generate Z1. So like that, 8 heads are there. So 8 heads are going to generate Z0 to Z1. Now these values are concatenated together and multiplied with your W0 to generate your output Z. So now we have talked about till this, right? So now we have completed the self-attention block. Now it has generated this Z1, Z2. So Z1 is an output for your X1. Z2 is an output for your X2. Then, as I already said, we took the input X, add it with Z, and then do normalization to get your Z1 and Z2. Now this Z1 goes to your feed-forward neural network. Same way Z2 goes to another feed-forward neural network. It's not the same network. It's a different network. Okay, here the weights are not shared. Okay, so here the weights are not shared. So here it goes to a feed-forward neural network. Same way Z2 goes to another feed-forward neural network, and this both runs in parallel. So what is this feed-forward neural network? So this feed-forward neural network is given here, right? So it consists of two layers, right? So two layers. One is layer 1. In layer 1, what we do is we increase the dimensionality of the input data. Okay, so that the Z dimension gets increased, right? For example, the Z dimension is 512, right? So this 512 is expanded to something like 1024 or 2048. Okay, so it is expanded. And after expanding, we are going to apply a non-linear activation function. So probably we'll be using GELU or ReLU. So GELU is nothing but Gaussian error linear unit. Okay, Gaussian error linear unit. ReLU is nothing but rectified linear unit. So Gaussian error linear unit is given by this equation. When you plug in the values, you will get a curve like this. So almost for negative value of x, you will get 0. For positive value of x, you will get a positive value. So this is the first derivative component of this GELU function. So for ReLU, so ReLU is nothing but ReLU of x is equal to max of 0, x. So if our x is negative, okay, for example, if our x is negative, it will be 0. It will be 0 for negative. For positive value of x, we will have the x as it is. Okay. So this is your ReLU activation function. You can see something similar. ReLU and GELU are almost similar in nature. Here the positive values, it follows the x values as it is. Whereas here it follows a tan h function, hyperbolic tangent function. That is the difference. So first we use a neural network to expand the dimensionality. Then we apply a nonlinear activation function. Then after nonlinear activation, there is another layer of neural network which reduces the dimensionality back to its original dimension. Initially, it got increased. Then we applied a nonlinear activation function. Again, then we try to bring it back to the original dimension. So this is what happens in your feed-forward neural networks. So that is what happens in your feed-forward neural network. So two important things. One is we take this Z1, increase the dimensionality, apply a nonlinear activation function, then again apply a neural network to bring back the dimension. Same thing happens for your Z2 also. Right? And then again it goes into a add and normalize block. Then we get the output Z1, Z2. So this is for your encoder 1. So this encoder 1 output goes as an input to your encoder 2 block. It goes as an input to your encoder 2 block. Again, in encoder 2 block, we have a self-attention mechanism and feed-forward neural network is the same repetition. So if I have the third encoder, the output of your encoder 2 will go to, as an input to your encoder 3. If I have encoder 4, output of encoder 3 will go as an input to your encoder 4. So like that it goes on. So when the final encoder is there, then it goes into a multi-layer perceptron, and this multi-layer perceptron is going to predict the output. So what is this multi-layer perceptron? Here I try to show you a neural network, a simple neural network, where we have this x1 to xn. This is nothing but the Z output from the top encoder. Okay, Z output from the top encoder is this x1 to xn. We try to assign the weights and biases for each neurons, and then your final output prediction is being carried out. So that is how this vision transformers are going to be used. Right? So here you can see we take an image, divide it into 9 patches, then this 9 patches enter with positional information. It goes into a transformer encoder, and then it goes into multi-layer perceptron, and the perceptron will produce a class label. What is there inside your transformer encoder? You can see a multi-attention head and then a multi-layer perceptron, which is your feed-forward neural network. So in the original paper, they have discussed about 6 encoders they have used. So that is how this vision transformers are built. And it is used in case of your image classification. Here right now I talked about image classification. It can also be used for object detection and semantic image segmentation. Let me talk a little bit about transformers also. Okay, this is related to vision transformer. In vision transformer, we only talk about the encoder part. The decoder part is missing. Whereas in a transformer is mainly used for generating text. Or if I want to do some machine translation from one language to another language, for Japanese to English or from Tamil to Hindi. So like that, when I want to do the language translation, we go with the transformer models. So how this is built? So the concept is similar. Only thing is, after building the encoder block, we will not have the multi-layer perceptron. So the encoder output will go to a decoder, and the decoder will try to generate the new text. Okay, we will see that in the next slide. So in a transformer, what we do, let us try to understand. Again, instead of image, here I'm trying to take text. Okay, thinking machine. So thinking is one word, machine is another word, right? So it is converted into a vectors, and then positional information is being added. Then it goes into a self-attention block, which I described just now. Then it goes into a feed-forward neural networks. Then subsequently, depending upon the number of encoders, it passes on. So you see here, see the difference here. Here we don't have a multi-layer perceptron, right? So the output of the top encoder, it goes as an input to your decoder, right? So here I have two encoders, so I should have two decoders, right? So the output of the top encoder goes to both the decoders. When you look at the decoder, it is similar to that of your encoder, right? So it also has a self-attention block. It also has a feed-forward neural network. In addition to this, right? So these things are common, right? So same procedure is being followed here also. In addition to your self-attention block and feed-forward neural networks, we have one more sandwiched layer, which is your encoder-decoder attention block, right? So this is something different when compared to your encoder. In encoder, we don't have this. In decoder, we have an extra sandwiched layer, which is your encoder-decoder attention. So the encoder information comes here. And this information is also used in finding the attention mechanism. Okay, encoder information is also used in finding the attention data. In our, based upon that, a new text is being generated. Okay? So that is the difference in your transformers. So in a decoder side, it is almost similar to that of your encoder side. So encoder starts by processing the input sequence. The output of the top encoder is transformed into a set of key and value matrices. So this is very important. Right? So here we get the output of your top encoder is what? Z matrix. So output of your top encoder will be, if I have two words, I will have Z1 and Z2. So we need to convert this Z1 and Z2 into two matrix. One is K and V, key and value matrix. How we can do that? Again, we take two matrices, one for key matrix, one for value matrix, multiply it with this to generate this new key and V matrix. So how to assign this weight matrix? This is weight for K, this is weight for V. Right? How to assign this weight matrices? First, initially, we will do it in a random fashion. So after multiplying, we get a key matrix and value matrix. So this key and value only will go as an input to your encoder, decoder attention block. From this decoder, I will get Q. Right? From this decoder, I will get Q. Whereas the K and V will be obtained from our encoder, decoder attention block. Then the other process is similar. By using this QKV, we have to determine a score, then scale down the value, then apply softmax activation function, then multiply the softmax activation with the value, and then add all those values to generate a Z. Okay, all this process are same as that of your encoder. Only difference here is now this K and V is coming from where? It is coming from your encoder block. Okay, so encoder says this word and this word has a very good relationship. Based upon that, the generation is also going to be changed. Right? So that is what we do in our transformer model. So the encoder decoder attention block helps the decoder focus on appropriate places in the input sequence. After finishing the encoding phase, we begin the decoding phase. Each step in the decoding phase outputs an element from the output sequence. So we will see in the next slide. You can see here during the first time step. During the first time step, so we have the Z matrix. Then we create this K matrix and V matrix, it goes to the encoder decoder. Then finally it generates a word during the first time step. Right? So this is for first time step. So we have taken some sentence in French. We embedded it as a vector, put the sequence information, then it goes into the encoder 1. Encoder 1 output goes to encoder 2. It generates a Z output. From the Z output, we try to generate this K encoder decoder matrix and V encoder decoder matrix, give it to a decoder, then generate the output from the help of a decoder. So this is for first time step. In the subsequent time steps, what happens? The output which is generated earlier is also given as an input to our decoder. Okay, so that is what happens. So here you can see here, in addition to this, the previous output is also given. You can see here, the previous output is also given as an input to your decoder. So this is during the other time steps, second, third, fourth, fifth, sixth. During the first time step, there is no earlier data, right? In the first time step, I is generated, right? So during second time step, this I is given as an input with the positional information. During the third time step, what happens? Now I is also given, am is also given as an input. Right? So like that, the generated data is also provided as an input to your decoder for generating the subsequent part. You can see fourth time step, it generates student. During the fifth time step, the student is also given as an input. Now it produces end of sentence. So now the machine has translated your French statement into a English statement. Finally, how these words are being generated, right? So that is the important question here, right? So you can see here, all are vectors, right? So the decoder generates again Z1, Z2. It goes into a linear and softmax layer. So this linear and softmax layer is the one which is going to convert this vector output, decoder vector output, into a text. Now we will see how this linear and softmax layer is going to work. Right? How this generates from the decoder output, how it generates the words out of it. So the final layer, linear layer and a softmax layer. So the decoder stack outputs is nothing but a vector of float numbers. Right? So how we are going to turn it into a word? We are going to simply project this Z, right? So we are going to simply take this Z, right? Some dimension data, project this Z into a bigger vector. How this bigger vector is formed? It is formed based upon the vocabulary of our language. Vocabulary of our language. Let us assume we have some 10,000 words in our English, right? So each vector element represents a word, right? So let us assume that our model knows 10,000 unique English words. Then we create 10,000 cells wide logic vector. So this vector is called as logic vector. So we transform this Z into this logic vector. How to do that? We use fully connected neural network here. Okay, we give the Z to a fully connected neural network, and this neural network will project it to a logic vector. Then, after projecting it to a logic vector, we need to convert that value into a probability score. right? For that, we use a softmax activation function. So, which means for each word, a probability score will be determined. For each word, a probability score. If I add all these things, I will get 1, right? The probability score will be determined. Then whichever word has a higher probability, okay, for example, in the first case, I might have the highest probability. So this I is coming as an output. During the second timestamp, what happens? Am some other position. So this has a highest probability. So this comes as an output. Next time instant, A might have the highest probability. So this comes as an output. During the next time instant, the student might have the highest probability. So this is going to come as an output. So that is how the decoder output. So the decoder output is a vector. So this vector gets converted into a text information with the help of a linear and softmax activation function. So linear in the sense, we try to project this decoder output to a logic vector with the help of a fully connected neural network. Then to convert this logic vector into a probability score, we try to apply a softmax activation function. So this softmax activation function will give the probability score. Then the algorithm will pick the word which has the highest probability and it will be provided as an output. So that is what happens here. We take the decoder output, give it to a linear layer. So this is fully connected neural network. It is projected into a logic vector. This logic vector depends upon the vocabulary size of the language. Then it goes into a softmax activation function. So where the probability score is assigned, then we try to take the label with the highest probability. That will be generated as an output. Right. So that is how a machine translation is being carried out using a transformer models. Okay, so let me summarize. First, we started with a vision transformer. In a vision transformer, what we do? We take the input image, divide it into patches, then we sequence the patch, then we add the position information. Remember, the position information is nothing but a pattern given, gets added with our input data. Then it goes as an input to your self-attention block. So in self-attention block, we try to find the relationship between the patches and it generates an output. It goes as an input to your feed-forward neural networks. So this feed-forward neural networks will produce an output. So that encoder output, lower encoder output will go as an input to the subsequent encoder. And the final encoder, right, the output of the final encoder will be given to a multi-layer perceptron to predict the output. That is in case of your vision transformer. In case of your transformer, the encoder part is similar. Only difference is the multi-layer perceptron we are going to remove from the final layer, right? So the top encoder output, we convert it into a key matrix and value matrix, and we give it to a decoder blocks. So the decoder blocks, if I have 2 encoders, I have to have 2 decoders. And in the decoder block is also similar to that of encoder. The major difference is, in addition to your self-attention block and a fully connected neural network, in between you are going to have a encoder decoder attention block. So this gets the information from the encoder, and based upon that, the new words are generated. So that is how the machine translation is being carried out. Thank you for your kind attention. If you have any queries, please let me know.
Thank you, sir. Yeah, any questions from the participant side? If you have any questions.
Somebody raised their hand, madam.
Yes, okay, I'll check. I mistakenly raised.
Okay.
Yes. Yeah, Dr.
Vijay,
Kambala Vijay.
Vijay Kumar.
Dr. Vijay Kumar, sir, do you have any question? Yeah. Any other participants? If you have any questions, please raise your hands. No? Yeah, Gokila. Yes, ma'am. If you have any question, you can ask. Yes.
Yeah, good afternoon, ma'am. Good afternoon, sir.
Good afternoon, ma'am.
Sir, actually, the session was very interesting and mathematically, I really liked it. You have gone through very detailedly, sir. So, as you have explained about the vision transformer, we have DETR transformer, right? Some deduction transformer.
Yes.
Does it all follow? Does it also follow the same logic like what you have given?
This is
What you have
this is for classification part, ma'am. So whatever the transformer which I have described here is for the classification part. There will be certainly some changes will be there for detection and the semantics image classification, or it will be different, little bit different.
Yeah, the
Majority of the
mathematics
concepts will
that
be same.
is mathematics that is behind the transformer is going to be the same. That is what my doubt, sir.
Yes, ma'am. Attention and all it will be same, ma'am. Attention
Oh,
mechanism will be same.
okay. Maybe the probably the
Finally,
encoder part,
in
decoder part.
deduction part, based upon that attention module, they will try to put a bounding box.
Yeah. Okay. Okay, sir. Thank you so much, sir.
Yes.
Yes. Thank you, ma'am. Any other question? Yes, if you have any questions, you can ask, and even you can contact sir. Sir has given you his email ID. You can even email him so that he will clarify your doubts. So if there is no other doubts, I can conclude the session. And on behalf of everyone present, I hope you have all enjoyed the session. I would like to express our sincere gratitude for your insightful and truly exceptional session, sir, on vision transformers for image classification. Your clear explanation of such a complex topic, like how it was started, was both informative and engaging. We greatly appreciate the time and effort you put into breaking down the key concepts, like from the mechanics of image patching to the intricacies of transformer code encoding and positional embeddings. Your ability to connect the theoretical aspects with the practical applications in computer vision has left us a deeper understanding of the subject. So the detailed breakdown of self-attention mechanism, how multi-ed attention forms, and how multi-layer perceptron plays a vital role here, it was really valuable, and it will influence the people for our research work, future work in this research field. So once again, thank you for sharing your expertise with us, sir. We look forward to more sessions and opportunities to learn from you. Thank you, sir.
Adding with Agila ma'am, I am also thanking you, sir. It was a wonderful session where we have understood much about this text and the image generation process, along with its various, how the transformers working behind all these things. Thank you, sir.
Thank you. Thank you. Thank you for
Yes.
giving me this opportunity.
Thank you, sir.
Thank you, sir. Thank you.
Madam,
Madam,
participants, please hold on. So we'll be having the next session in a minute.
our
Ma-
resource person, Tinagra.
Yeah. So good evening, sir.
Also have
Tinagra
joined
Perumal,
us.
sir.
Yeah, good evening, ma'am. Good evening.
So
So
now,
can we have your video on, sir?
Yeah, just hold
Yeah.
on. I'm going to get on.
It's our great pleasure and honor to welcome our next speaker, Dr. Tinagra Perumal, sir, to this 6 days online FDP on demystifying transformers, the brains behind generative AI. So now I would like to invite Dr. Anita ma'am to introduce our speaker.
Thank you, ma'am, for giving me this option of speaking about our resource person, Dr. Tinagra Perumal, sir. Welcome you, sir, for our FDP. So, Tinagra Perumal, sir, is working as an associate professor and head of the Department of Computer Science in the University of Putra, Malaysia. And he is a recipient of 2014 Early Career Award Consumer Electronics Society